Hello everyone, my name is Ashutosh and I am the teaching assistant for NPTEL's Fiber Optic Communication Technologies offered by Professor Deepa Venkitesh from IIT Madras. Today we will be discussing the week 10 of the lecture series. The topics discussed in this week. The brief outline is we spoke about some of the non-linear effects. In the last week we had covered the self-phase modulation. This week we looked at the cross-phase modulation. Then we looked at some of the non-linear processes such as the four-wave mixing and why phase matching condition is important for the four-wave mixing, and how dispersion, which was earlier inhibiting our transmission, becomes useful in these contexts. Then we looked at some of the scattering losses. There were two types, elastic and inelastic. We looked at the Stokes and anti-Stokes phenomena. So if this was a center wavelength, this size was Stokes and this size was anti-Stokes. Then we looked at the stimulated Bernoulli scattering. We looked at the acoustic phonons, the electrorestriction, the phase matching condition, and then we looked at the spontaneous and stimulated scattering. When the incident power becomes very large and these become kind of self-sustaining just like a laser, and you see an exponential increase, that is when spontaneous turns to stimulated. We looked at the Stokes spectrum and we looked at SVS limiting the power after a point. This is slightly, there is a typographical error here. This is limiting. SVS limiting the power at the receiver because most of it was getting back to the transmitter itself, and this starts at around 10 milliwatts. And that is why you will see that in most of the actual deployments, this is the input launch power is 0 dBm. And after that, we looked at simulated Raman scattering, and this is because of the molecular vibration. Sometimes it is called optical phonons as well, and no phase matching condition is required around it. This has a comparatively higher threshold of around 500 milliwatts of optical power, and this is used primarily in the Raman amplifiers. The amplifiers made using this is used primarily in the optical submarine links, where the transmitted fiber itself acts as an amplifier when we put wavelength light into it, and this is usually 100 nanometer lower than the transmitted power. So if we are transmitting at 1550 nanometers, our launch will be 1450 nanometers, like this. And then we saw the Shannon's information limit and how nonlinearity was affecting it at higher powers. Then after we had finished the nonlinear aspects of it, we looked at some of the components that are necessary for link design. We looked at some of the performance metrics as to how we characterize these components. There were insertion loss, excess loss, and the crosstalk. And we looked at some of the usual components that are used in the network, which is a 2x2 coupler, N-cross-N coupler, and it could be N-cross-M coupler as well. So N-cross-M, like multiple different numbers of input at all. Say I have two inputs and I can split it into 4 pieces. Or I have one input, I want to split it into 2. So this would be called 1x2, this will be called 2x4. So this is N cross, this can be N cross M. And then we looked at how wavelength division multiplexing works. We looked at some of the other optical components such as VOA, which is variable optical attenuator. It can either be controlled electrically or mechanically. Then we looked at how some of the polarization controllers such as the metal clad polarizer, the polarization controller. We looked at Faraday rotators and how they are used in making isolators. Professor Deepa talked about polarization sensitive and insensitive, both kind of isolators. Then we looked at an important optical component called a circulator. Then there are some different kinds of filters such as wavelength filters, tunable filters, fiber Bragg grating. OADM is optical add drop multiplexers, in which you select a particular wavelength. Then we looked at wavelength selective switches, and then she also talked about wave shapers. Now for the sake of completion, I have added some of the formulas that we used even last week. They have just been mentioned here, and we might be referring to them while solving the numericals. And the formulas that we dealt with in this week the formula for the cross phase modulation, where the non-linear effect, where this is the chi3 one, because if you remember from last lecture, there is a linear term, and then the chi2 is absent because the fiber has cylindrical symmetry, and the next non-linear term that is present there is the chi3 term. So we have the chi3 coefficient, and this is how the electric field the non-linear coefficient looks like for omega 1 and omega 2 launched into the fiber. Then we looked at the four-way mixing process. This is the phase matching condition for the four-way mixing process. We looked at the Brillouin scattering. The frequency she had realized in the class that they are usually 11 gigahertz apart. And then we looked at the Raman scattering, and these are the formulas that we'll be using in the numericals. Now, for formulas pertaining to the different components that are present, we looked at an optical coupler. If you remember, an optical coupler is just a 2x2 device, port 1, port 2, port 3, port 4. Actually, this is made as it was shown in the slide, is you have this fiber going here, and then this is your effective interaction length, and depending on how long this is, the ratios are dependent, and the power at port 3 and port 4 are dependent, given by this formula, and this is the electric field matrix that relates the input to the output. Now the split ratio is decided by P3 divided by P1 per P2. Excess loss is the loss in the component that is other than that is just because of the material imperfections that are there. And the insertion loss is the ratio of the output power with respect to the input power. The negative sign is there is just because Pj is always lower than Pi. And then we looked at how the polarization controller is made by having 3 circular hoops, and then it's lambda by 4, is lambda by 4, lambda by 2, lambda by 4. So with the help of these circular things, we are making a quarter wave plate, a half wave plate, and then a quarter wave plate. We looked at the Bragg condition, which is used in the fiber Bragg gratings after that. Now let us pay attention to the first question that we have from the assignment. The question goes something like, given GR is 1 e raised to the 110 raised to the power minus 13 meter per watt, and GSBS, SBS is stimulated. Scattering for length of 80 kilometer, alpha of 0.2 dB per kilometer at 15 mm. The SRS threshold is, now R is Raman, B is Brillouin there. So now to solve this question, we will have to first take the coefficient which is given in alpha. The loss coefficient is 0.2 dB per kilometer. We have to bring it in the linear scale, and if you remember from the last week, we had 0.2 into 0.23 per kilometer. Let me just pull out my calculator. This would be equal to 0.046 per kilometer. Now from this, we'll try to find the effective length of the fiber, which is given by formula LE effective Now here alpha is the loss, L is the length of the fiber. Now if we substitute these values, the distance that was given to us was 80 kilometers. If I just do this math real quickly, Now if we solve this, we are getting the answer of somewhere around 21.19 kilometers, which is equal to 21.2 kilometers. So this is the effective length that we have, and we have SRS threshold. The formula for this can be found from our formula sheet, where SRS threshold is given by this formula here, 16 A effective GR L effective. Now SRS threshold, if you write it for this, P threshold is given by 16 A effective by GR L effective. Now we still do not know what A effective is. A effective for a single mode fiber, single mode 1550 nanometer fiber, is about 50 micrometer square. So that here, if we just substitute all of these values, the value of GR 1 e raised to the power minus 13. Let us quickly do this. We are left with 10 raised to the power minus 1, so this becomes 10 raised to the power 2. And the value that we'll get will be 0.377 watts or 377 milliwatts. Now if I want to convert 377 milliwatts into dBm, so P G SRS threshold 10 log 377 milliwatts divided by 1 milliwatt would be 10 log 377, which is 25.76 dBm. The reason I had come this way and not left it at milliwatt is because in the question, two reasons. Because in the question the options were given as in dBm, and second, it is usually the natural convention, instead of dealing in milliwatts we deal in decibel scale, because gain and loss just becomes addition in the long scale. Now let us look at the second question. The second question is very similar to the first one, where we have to find the SBS threshold, and B here corresponds to balloon. Now to find this question, we again go back to our formula cheat sheet that was created for us in the slide, and we look at it. For SBS, it is, the factors change slightly, so it is 21 area effective by GL effective. So let us go back here. So the formula to be used slightly changes. And we go PSBS threshold. This is given by 21 area effective by G. Because we are doing SBS, that's the coefficient that will come here, and this is the same L effective. So 21 into 50 micrometer square. Now GSPS, if we go back to the question, is given as 5 into 10 raised to the minus 11 meter per watt. So we have 5 into 10 raised to the minus 11, and the L effective that we had calculated was 21.2 kilometers. If we solve all of this, we're left with 21 into 50 Now this is because micrometer square is 10 raised to the power minus 6, square is 10 raised to the power minus 12. That is why here instead of 10 raised to the power minus 6 I am writing 10 raised to the power minus 12, and that is divided by 5 into 10 raised to the power minus 11 into 21.2 into 10 raised to the power 3. This becomes 10. This is 10 raised to the power minus 1, so this goes away, and we are, so this is very close. So this is 21, this is 21.2, and this is 10 raised to the power minus 3. So we are actually very close. We would get 21. So let's take this 10 raised to the power minus, this is in watts, let's take this 10 raised to the power 3 out, and we'd come to milliwatts, and that means we would be left with 0.99 milliwatts. And when I convert it into dB scale, BSGH this would be minus 0.043 dBm, and that is the answer for the second question, which is minus 0.04. Second one, the last one. Now let us move on to the next question. The next question is, in this week we had studied the X here represents the cross, so this is the cross phase modulation, and this is the self phase modulation. Now the question is asking the strength of X phase modulation is how many times the self phase modulation. So the first question is it greater or is it lower? So you remember that the self phase modulation was one wavelength moving into the box, and then because of the changing intensity inside and the changing refractive index, the behavior was changing. But for cross phase modulation, what we saw was we were inputting two wavelengths, omega 1 and omega 2, and then whatever was happening inside this box. This is captured here in the notes by the formula for this cross phase modulation. You will see here that we have omega 1 and omega 2, two lights coming in. This is a tube of it because this is the third order factor. Now when you expand that third order factor, it is a normal algebraic exercise where you do a plus b plus c, or actually a plus b whole cube, and then you will be left with the terms such as 3e1 square e1 e raised to the power j omega 1 t minus beta 1 z, and there would be a second term Professor Deepa had written in the, it was shown in her slides as well, where there would be a second term where there is 3e2 square e1 e raised to the power j omega 1 t minus beta 1 z. So one thing to note here is that the frequency omega 1 is being expanded by the fact of electric field first of the and the electric field of the second, and you see that the ratio here is 2 times. So the answer here is that the strength is twice that of the SPM. Now let us look at the next question. The next question is, a coupler is to be constructed from two fibers by fusing. This is the same exercise where two fibers were brought together and then they were twisted such that some overlap was happening between the electric fields. Given the coupling coefficient K of 2 per meter, what is the minimum coupling length required for the coupling ratio of 50-50? Now the question is, you have P1, P2, P3, P4. Now K is given to us as 2 per meter. What is the coupling ratio? So we know that from the formulas you can see in the sheet as Pz, P3 is given as P1 cos square Kz, and P4 is equal to P1 sine square kc. Now because we want the coupling ratio to be 50-50, that means cos square kc is equal to sine square kc, or cos square kc minus sine square kc is equal to 0, and this would yield, or we could have simply, when is cos kz plus minus sine kz, and this condition is only satisfied for the case for pi by 4 or 30 degrees. So this condition is only true when the argument factor kz is equal to pi by 3. Is it pi by 3? No, this is pi by 4, because you want 180 degrees by 4, which is 45 degrees, and that would mean z is equal to pi by 4 into k, which is pi by 8. So this is true for a minimum length of pi by 4, but this can be in multiples of this, because as this equation is satisfied by kc pi by 4 into m. So for all the, so this condition is satisfied by m pi by 8, because the trigonometric identity is being satisfied with pi by 4 or 2 pi by 4, which is pi by 2, and this is how we will move forward. Now the second question, now the fifth question is, which one of the below components can be used as WDM demultiplexer to extract a single channel? So WDM here is wavelength division multiplexer. Now before we get into that, the WDM multiplexing is either, then it is further classified into two kinds, which is dense wavelength division multiplexing. And in this, the channels are separated by 50 gigahertz band, and this is defined by the ITU grid, and this is what she was Professor Deepa was talking about. It starts somewhere from 1530 to 1570 nanometer, and there are 80 channels. So 80 channels are there in WDM. There is another type which is coarse wavelength division multiplexing. This is DWDM and this is CWDM. Now let us look at the question that we have at our hand, which is, which of the following components can be used as a WDM multiplexer? The first is an isolator. Let us discuss each of the components. An isolator is an optical component that allows for light to be propagated only in one direction. We call this port 1 and port 2. Light is allowed from port 1 to port 2, but from port 2 to port 1 is not allowed. So clearly this unidirectional flow of electric field is not what we mean by extracting a single channel. The second is tunable band pass filter. Now what is a band pass filter? A band pass filter in the usual sense of the term is that there is a band of frequencies and it only allows for a single frequency to pass. So if this is the entire band, it will only allow one of these bands to pass. So on the output side it will just be at this band, and this does sound like we are extracting a single channel out of it, but for the sake of completion let us look at the other options present there as well. What is a circulator? Circulator is a optical component. It is usually either a 3-port or a 4-port component in which both are numbered this way. Whatever is coming on port 1, whatever is coming on port 2 goes here, comes out on port 2, and whatever is coming from port 2 goes here and comes out on port 3, does not go back on port 1. So it is kind of circulating the light. It is like redirecting the flow of light from port 1 to port 2 and port 2 to 3. And this is the circulator. And the fourth option is Faraday rotator. Now Faraday rotators are just materials that in the presence of magnetic field, the polarization that is rotated is not unitary. So if you have a light this way and magnetic fields are this way, north, south, and if say the light is rotated by some angle theta, if you send it back, it is not be a unitary transformation, and this is what is used to make the polarization sensitive or insensitive isolators, because it is twisting the polarization of the light itself. So the correct answer for this question is the tunable band pass filter. Now let us look at the next question. Next question is, a combination of which of the following components can be used as an add-drop multiplexer? Isolator and circulator, fiber Bragg grating and coupler, polarization controller and isolator, fiber Bragg grating and circulator. Let us look at the ones and let us just eliminate here which we think cannot be possible. Isolator and circulator. Isolator allows for unidirectional flow of light. So clearly this cannot function as an add drop multiplexer, because even if we come up with a clever scheme to drop something, we cannot add it back into the network. That means, let's say I have a network here and then I am a user. Let's say I put an isolator here and then some complicated scheme of circulator. I put a circulator here and then let's say I put an isolator. So whatever is going here from port 1, it will port 2 and it will go forward, but whatever is coming back, the isolator will not allow it. So this is clearly not the answer. Now let us look at fiber Bragg grating. So we had discussed what a fiber Bragg grating was. It was just a strip of fiber and certain sections of it were illuminated by different lights, so the refractive index was changing periodically. And because of this feature, some of the light that was coming this way, and if you feed a wide enough spectrum to this, on the output what you will have is you'll have the spectrum and then a narrow part of it, depending on the Bragg grating, is reflected. So this is transmitted, this is input and this is transmitted, and what is reflected would something be like this. Hold on, sorry. What is reflected would something be like this. The exact, these two would make up, combination of these two graphs would complete this graph, barring the insulation loss. So it does look like the fiber Bragg grating is the component that will help us drop and add the channel, and there is no sense of directionality here. So but the problem is coupler is not the right solution. So what happens, let's say I have an FPG. Now I will draw this as fiber Bragg grating. So what a coupler will do, let's say I put a FPG, let's say I put a coupler, let's say it is a 2x2 coupler, and I've put a FPG. Whatever is going this way, I'll be able to have it. This will reflect certain wavelength and it will come here, but it is not going in the forward channel. So if this was a metropolitan link where there was this one, if this was a metropolitan link where there was one fiber, what I am effectively doing, and this is your TX and this is your RX, what I am effectively doing is I would be able to tap some out of it, but if I just use a coupler, what is happening here, let me use another ink color. So light that is going here, it is a wide spectrum. So first the wide spectrum will go here, and the wide spectrum with this notch will come here, and this will be reflected to both the sides. So this is input, this is port 3, this is port 4, and this is reflected. So you see, this is not really adding or dropping on the link as well, the entire link. But we understand that fiber Bragg grating is the solution. Polarization controller and isolator is the steps. Polarization control, changing the polarization will not help us add or drop. And that way we are left with the final answer. So by the option of elimination, we know that this would be the answer, but let us see how this can be constructed. Let us say I have a circulator, port 1, I put the FPG here, and this will be port 3, this will be port 2. Now let us inspect what is happening. Let's say I have this is lambda, this is power, and it's a wide spectrum that is inputting in port 1. What will happen at the fiber Bragg grating is it will take this entire thing and then it will transmit this part of it, and it will reflect this. Now what happens to this reflected thing? This goes here, and remember, reflected goes here. So in this way, the third part will just, now if there was a line and we had a, or let us say if we had a fiber line, and if I put a circulator here, 1, 2, 3, and there was a FBG in this case, and this went on, and this was 3. So if TX was transmitting a wide wavelength, what will come out, the entire thing will go from 1 to 2 at the FPG. This will transmit the entire thing, dropping a wavelength, and whatever is reflected here will come in. And in this way, we will be able to add or drop one wavelength. So the correct answer is the fourth one. Now let us look at question number 7. Question number 7 is, it is impossible to build a device that combines all power from 2 input ports to the third port without loss of the given, without loss with the given scattering matrix given by, we have been given this matrix, and it is asking for a reason. So whenever the scattering matrix is given, think of it this way. If we are assuming without loss, that would mean that the adjoint of this scattering matrix multiplied by each other should give me the identity function. So if I have S given here, if I take this, so if I have S given here, which is given by 0 0 S13 0 0 S23 S31 S32 S33. Now what energy conservation means, essentially means is that SS dagger should be identity, and if I have these matrix written out, and the complex conjugate of these numbers would be now if I just carry out the multiplication here, how do you multiply matrices? Row and column, row and column, row and column. These would give me the first element. So this would be S3. Hold on, I seem to have made a mistake. Whenever we are taking the S dagger, this is the, you have S matrix and you transpose it and then you take the complex conjugate of that thing. So if I transpose it, this would be 0 0 S33. This element S13 instead of here will come here, because in transpose that is what we do. So this would be S. Or did I write the matrix incorrectly? I think I have written the matrix incorrectly. So we will revisit this question. Now let us look at the next question. The next question that we have is, it is impossible to build a device that combines all optical powers from two input ports to a third port without loss. There should be a comma here, without loss, with a given scattering matrix. This is the scattering matrix, and because. What are the reasons? Now whenever we are given a scattering matrix and we have to assume conservation of energy, we have to assume that S dagger S or SS dagger is equal to identity. Now it has been given to us that S is equal to zero zero S13 0 0 S23 S31 S32 S33. Now its dagger is 0 0 S13 0 0 S23 S31 S32 S3. And if we solve all of these, and we have to equate it to 1 0 0 0 1 0 0 0 1. When we equate these, we would see that it is impossible to satisfy all conditions, and hence energy conservation is violated. So the correct answer for this is it cannot satisfy the conservation of energy condition. Now let us look at the next question. Next question is, consider a 4 cross 4 switch shown in figure 14. This is supposed to be the figure 14, made up of 2 cross 2 switches. Suppose each 2 cross 2 switch has a crosstalk suppression of 50 dB. Assume for now that powers can be added and that we do not have to worry about individual electric field adding in phase. Now because we do not have to assume individual electric field being adding in phase, this makes our life very simple. Now we have a 4 cross 4 switch with a crosstalk suppression, crosstalk of 50 dB, or effectively not crosstalk suppression of 50 dB. Now what is 50 dB in the linear scale? 50 dB is 10 log P out by P in, which is, now because this is suppression, it comes with a negative sign, and this essentially means 10 raised to the power minus 5. So what this means is that the leakage from each channel into the other, 10 raised to the power minus 5. That means that essentially if you have 1 2 3 4 2 3 4, if light is going on in this, 10 raised to the power minus 5, 10 raised to the power minus 5, 10 raised to the power minus 5 will be coming here. Now if this is happening in all the 4 cases, what would happen is 1 would be the correct, because I do not assume any leakage here. So let us take this specific line from example. If This leakage is present in all the circuits. The number of incorrect optical paths that would be getting there would be 3 into 10 raised to the power minus 5. Now, if my effective suppression was 50 dB in the original, and then we have 3 into 10 raised to the power minus 5, that would mean this is being degraded by 50 minus 10 log 3, which would be equal to 45.2 dB. So this would mean that what is the what is the overall crosstalk suppression? The overall crosstalk suppression is 50 minus 10 log 3 into 10 raised to the power minus 5, 1 for each channel, and this is equal to 45.2 dB. If you want an overall crosstalk suppression of 40 dB, what should be the crosstalk suppression of each switch? Now, if you want the crosstalk suppression to be of 40 dB, and then we know because of each switch there would be crosstalk suppression of 10 log 3, and this would give us to 44.7 dB. So if we want an overall suppression of 40 dB, we only need a crosstalk each switch suppression of 44.7 instead of the 50 shown in the previous case. Now let us look at the next question that we have in our line is product sheet for a 2x2 single mode biconical tapered coupler. This is the kind of coupler that we have talked about. With a 40-60 splitting ratio sheet that says that the insertion loss are 2.7 dB for the 60% channel and 4.7 dB for the 40% channel. If the input power P0 is 200 microwatts, find the output levels P1 and P2. Now, we know that the insertion loss minus 10 log P out by P in, or insertion losses minus 10 log P out by P in, or you can have it as 10 log P in by P out. All the numbers have been given to us. All the numbers are given as 10 log 10 of 200 minus 6 watts, and let us say I want P0 to be calculated in microwatts, and this has been given to us as 2.7. So this comes out as 200 into 10 raised to the power minus 3 divided by P0 is equal to 10 raised to the power 0.27, or and this would come out as 200 into 10 raised to the power minus 3 is just 0.2 divided by 10 raised to the power 0.27 is 1074. $107.4. .074 milliwatts, and that corresponds to microwatts. Similarly, we could attempt for the other side as well, but I don't think that is required in this case. You can attempt for the, so for this I attempted for the 60% side. You can attempt while solving for the 40% side and see if you are arriving at this number or not. Find the excess loss of the coupler. Now excess loss, Now I know that the correct answer, I'll utilize that. The correct answer is P1 is 107.4 microwatts. From the option, P2 is given as 67.8 microwatts. Now access loss. Excess loss is whatever is the optical loss of the component that cannot be retrieved in any other way, and that is given by 10 log with the base 10. This is P input divided by P1 plus P2. Everything is in microwatts, so it's simpler. 10 log 10. We were inputting 200 milliwatts of microwatts of light, and we got 107.4 on one and 67.8 on one, and this equals to 10 log 10, 200 divided by 200 divided by 175.2, and 10 log of 200 divided by 0.2, and this is equal to 0.5749. The closest answer here is 0.58, so that is the correct one. Now let us consider two periodic filters, one with period f1 and the other with period f2. Assume them to be integers. In other words, the first filter selects frequency mf1 where m is an integer, and the second selector fills mf2 if the resulting cascading filter is a periodic, and the period is given by. Now this is kind of an intuitive question. If I have one filter that selects these wavelengths, okay, let's say I have another filter that selects every other wavelength, what are the wavelengths that will be transmitted if I cascade these two? This, and how did I arrive at this number? This is a basic mathematical function called least common factor. So the answer for this is least common factor. Now the next one makes my point more clear. If the period of two filter are, one of this is 500 gigahertz and the other is 600 gigahertz, then the cascaded structure will be a periodic with a period of. Now this is not similar, right? This is, let's say this is my 500 gigahertz, okay, and let us say that I take the other one as my 600 gigahertz. So from the beginning, let's say this was the beginning, so it would be slightly off here, that would be slightly off here. Think of, if we start numbering, this would be 500, 1000, 1500, 2000, 2500, 3000, 3500, and when I start doing this, this is 600, 1200, 1800, 2400, 3000. So you see, if I cascade these two filters, only this is being picked up. And how did I arrive at this number? The LCM of 500 gigahertz and 600 gigahertz is 3000 gigahertz, because that is the least common multiple of these two numbers. So to only allow these frequencies, let's say even the second one allows this one, even if the first one allows this one, the second one would not allow it, or if there is no light for the second one to allow at this point. So that is why both of them have to overlap for them to transmit together. Now let us look at this question. This is given: optical power launched into a 10 kilometer single mode fiber through a 2x2 coupler is 1 milliwatt, as shown in the following figure. The fiber coupler has a 10 dB power coupling ratio. Alpha is equal to 0.1, we usually refer to as a 90-10 coupler or 10-90 coupler in this case, and has no excess loss. So this is the ideal case. The refractive index of the fiber core is 1.5. I seem to have accidentally cut the call off. Let me log back in. Now let us look at question number 12. We have been given optical power launched into a 10 kilometer single mode fiber through a 2x2 coupler is 1 milliwatt, as shown in the following figure. The fiber coupler has a 10 dB power coupling ratio, or as we call it, a 90-10 coupler or a 10-90 coupler. So one side takes 10% and the other side takes the 90% of the input, and it has no access loss. That means this is an ideal case. The refractive index of the fiber core is n is equal to 1.5. The fiber pigtail at port C is AR coated. That means there is no reflection from that port, and the far end of the 10 kilometer fiber is open in the air, cleave perpendicular to the fiber. The isolator assures only unidirectional transmission and their losses are negligible. Okay. So what is happening here is some power is being launched here, and the power in this case is 1 milliwatt. So we have 1 milliwatt power being launched here, goes through the isolator, to port A, and because this is a 90-10 coupler, so assuming 10% goes here and 90% goes here, and because this is anti-reflected coating, there is no reflection from the facet, but because this is open to the air, and so the refractive index, because this is open to the air, this side the refractive index is 1.5 and this side is air, which has a refractive index of 1. So there would be some reflection here, and that would go back. Then it would again go 90% this way, and 90% this way and 10% this way, and whatever is output here. So let us look at the first question. Neglecting all fiber losses, what is the optical output of P naught? So this can easily be calculated as, let us see the reflection. So one thing to note here is, think of it this way: A to C is 10% and A to D is 90%. So along the same side there is 10% transmission, along the opposite side there is 90% transmission. So while going back, along the same side there would be 10% transmission, and along this side there would be 90% transmission. So the way we will calculate is P output is whatever is my P input. For the first side, 90% goes here, then whatever is my reflected power, and then the 10% goes through. That means I need to find the P reflected, or at least just the ratio of reflectance, which would be given by N2 Fresnel's law, which is N1 minus N2 divided by 1 plus N2 whole square, where these are refractive indices. So N1 is 1.5 minus 1 divided by 1.5 plus 1 whole square is 0.5 over 2.5. This is just 5, so it is 1 over 25. And that would give me the answer as P out is, my P in was 1 milliwatt. P in times 90 by 100 times 1 by 25 times 10 by 100, and my P in was 1 milliwatt. This 9 divided by 2500, which is 9 divided by 2500 milliwatts. And when I do it in log scale, this would be 10 log, and this is minus 24.43 dBm. Minus 24. So the closest answer here is 23.4 dBm, which is equal to minus 24 dBm. Now let us look at the next case. If the attenuation coefficient of the 10 km fiber is 0.25 dB per kilometer and neglect losses of the other fiber, what is the optical output? Now let us see where the fiber was actually added. Now the 10 km fiber is added here. That means the light is going 10 km this way, and whatever light is going reflected, that is being this way. Now the benefit of working in a dB scale is that all the losses just become additions and subtractions. So if we have a 0.25 dB per kilometer for a 10 kilometer length traveled twice, that is just 5 dB loss. And because I already know, so my P out prime would be P out from the previous case, and I will subtract another 5 dB in it. So in the last case we had P out as minus 24.4. Then I subtract 5 dB from it, and this is minus 29.4 dBm, which is this case. And with this we come to an end of this interaction session. If you have any other questions, feel free to post in the forum and I'll try to reply to them. Thank you.